should be live.
Ew.
The revolution will not be televised. It will be
Will be
live.
streamed.
Yeah, real quick, Gregory. Let's let them have a back and forth before you do that.
Yeah, let me give an introduction here. So I'm joined today here by ZZ Pop.
Hello, thank you.
He's in the academic field, and he wanted to discuss relativity of simultaneity, specifically the Einstein train and the bomb, and the example I came up with the balls. And I think we'll probably go over a couple other things or whatever. We'll see where it goes. But anyway, if you want to start us off.
Just because this one's so visual, would it be helpful to put something up on the screen of like the graphic you already have of like the train and the lightning strikes? Or, I mean, I could sketch something out, but just want people to be able to follow along, with what we're talking about here.
Boom.
Let's see. Sorry, and I'm just looking at the text chat here. Where do I
check out the stream?
Live stream?
Yep. By the way, you can also follow Oh, he left by accident.
Oh, word.
I'm glad this is going down.
I'm sorry. I clicked on the wrong thing.
Bump.
Okay.
Watch
stream.
By the way, if you want to follow along with
there we
what
go.
he's showing, if you want to follow along with what he's showing, this is all published on his Obsidian. I'll send the link.
Yeah, is my audio quality good enough for this? Just want to.
Oh yeah, you're solid. Sure. You're solid.
Yeah.
I'm gonna send it to
you. So this is the scenario of you've got lightning that strikes 2 points here, and there's one person who's stationary to the two trees where the lightning strikes, and then there's a train that's moving with respect to the two trees where the lightning strikes. And within the theory of relativity, from these two different perspectives, the lightning strikes. So it looks like in the first diagram you have here that they hit the two trees at the same time as seen from the perspective of person at point C, right? Because they're stationary to the trees and they see the lightning strikes the two trees at the same time, right? And then the claim is that from the perspective of someone on the train, though, they would see the lightning strike tree B first and then tree A. I remember exactly which way it goes here, but the point being is that, one of them sees the two strikes as simultaneous, the other one sees one strike as happening first, and then the other. Yep, so we're all caught up on that of kind of what the framing of this is. And then it seems to set up an apparent paradox of, okay, let's say you've got a bomb on the train, and the bomb explodes if it sees the flashes of light at the same time. So the question is, does the bomb explode or not? Again, there's a couple different ways that this could be set up, but Alan, is that the way you would set this up when you were originally presenting it?
Yeah.
You're muted, Alan.
Yep, pretty close. Pretty close.
Yeah.
You gave the like the mainstream explanation so far?
Yeah.
So basically you're saying all right, so to summarize, is your argument that the moving observer sees the sequence of events as an apparent effect, and when you account for the signal timing difference, that they'll all agree on the simultaneous event, like as an outcome?
As far as to whether or not the bomb explodes, yeah. So it's all going to come down to like where the detector is, like what is actually the mechanism that triggers the bomb. So the simplest version of this is that there's a detector on the bomb, and the detector needs to see two flashes of light at the same time in order for the detector to trigger the bomb to explode. So the main point here is that even though, let's say, person C does see the two lightning strikes, bam, at the same time, they also see that the flashes of light from those strikes don't hit the bomb at the same time. So looking at your first picture there, because the train car is moving towards tree B, it's going to run into the flash of light from the strike at tree B while it's running away from the flash of light at tree A. So it's going to hit the flash of light coming from tree B first, while it takes more time for the flash of light from tree A to catch up with it. So, like, the resolution to the paradox here is that, it doesn't matter that person C sees the two flashes simultaneously, and the bomb doesn't see the two flashes simultaneously. Like, person C will still see that the bomb saw the flashes at different times. Like, you can see how something looks from a different person's perspective, even though it's not how it looks from your perspective.
Okay, let's see the issue. Give me 1 second. Okay. So the issue, so you're saying that they'll both, like, in any scenario, right? It doesn't matter where the detector is, right? We could put it anywhere. That essentially, when you account for the timing difference after the signal is sent, that essentially the bomb will go off for both observers, right?
Yeah, because it's
Okay.
so I think the subtle point here is that nobody sees anything as it happens. You
Okay.
see it after a time delay of the light reaching you. And then saying that, like, from a given perspective an event occurred at a certain time is you inferring how far back in the past it must have occurred if you assume that the speed of light is constant and okay, it's this far away from me and I saw it at this time, so I'm going to subtract the travel time of light. So, like,
Okay.
one person can see the two
Yeah.
flashes reach them at the same time and also see that somebody else is in a spatial position where they won't receive the two flashes of light at the same time. But then if that other person takes themselves as being the stationary person, they do a different calculation of when the flashes must have originated in order for them to have received the signals when they got them.
Okay. So I see where the issue is here. So what's going on here is you think that by correcting for the timing difference after the signal is sent, that is adequate, and that will lead to the agreement on on reality that the event actually took place simultaneously, because we can confirm that, right? So we can set up different ways to confirm that. So the issue here, what I'm going to refer to, what we're going to start with, is 2002, a paper by Schur and others titled "The Challenge of Changing Deeply Held Student Beliefs About the Relativity of Simultaneity," because you're actually at a contradiction to the theory here, and we're going to start with what they note on. So this paper is about how they interview different students at different levels of education, that study relativity, so postgrads, undergrads, etc. And it says here, I'll read from, it says, "Yet many of these students have the deeply held belief that simultaneity is absolute when the signal time is accounted for all observers, and the reference frames agree in the time order of the two events." So you are conflating causally linked events with spatially separated events. So time is independent, and it's observer dependent. So spatially separated events are not causally linked. So they're actually going to lead to two different outcomes. So the correct interpretation of the train scenario or bomb scenario or the ball scenario is that it is mandatory that two separate outcomes occur.
Just
Because
to clarify, I wasn't saying
we
that this all comes down to just the time delay in light. That's part of it. The other part of it is that in order for two observers to both claim that the speed of light is the same speed, they have to be using completely different coordinate systems for space and time. So that's, time dilation and length contraction. My main point there is that the thing that they're disagreeing about regarding simultaneity is when the lightning strike struck the tree, but not when the flashes of light reached the bomb. That's, it's a separate question. from the bomb's perspective, the flashes of light from the trees of the lightning strikes didn't occur at the same time, and from the person observing its perspective, they did occur at the same time. So there's a disagreement about when the lightning strikes hit the trees, but the person at point C doesn't disagree that the flashes of light from the lightning strikes reach the bomb at different times, because from their perspective, like, bam, the lightning strikes hit the tree, and the train is moving towards tree B. So the train's going to catch up with the flash of light from tree B first, and it will take longer for the light from tree A to catch up with the train, because the train is fleeing away from the flash of light at tree A. So, like, person C understands that from the train's perspective, they're going to see the flash of light from tree B first, and the flash of light from tree A second. So it's the thing. It's not in contention as to when each observer sees the flash of lights. What's in contention is the order of events of when the lightning strikes occurred.
Well, what's in contention is the validity of the frame in which the sequence of events is that valid in. Because if all inertial frames are equally equivalent, are equal and equivalent, then you have to have two separate outcomes, because the sequence of events in that frame must be valid. Otherwise, you can't have reciprocity in the transformations, meaning you can't show that for the stationary observer, the bomb doesn't detonate because of motion, and in the moving frame, it does detonate. You can't do that otherwise, which is the whole point of the theory. So I want to take us back to Einstein real quick, and then add a couple supplements to this argument to show that the interpretation demands physically different outcomes, because otherwise this theory doesn't say anything different about absoluteness, right? Because remember, the classic theory was built on absolute something, right? It's either the barycenter, or it's the fixed stars, or it's the mass distribution of the universe. Somewhere out there's an absolute something that all of this is relative to. So in order to get away from that, right, we have to have something that's not the same, right? So mutually exclusive, like a different thing. So to be different from what's already the thing, absolute simultaneity becomes relativity of simultaneity. So what Einstein is saying here at the beginning about the frames being valid for his first postulates, and it goes on to talk about how he's removing the ether as a mechanism and a mathematical concept, where he's not going to assign imaginary vectors to points in space and all that stuff. Let's see here. So anyway, we'll go down to simultaneity, the definition of simultaneity. Now, this is really important here, because this is how we're going to define time. So remember, I know it sounds contradictory and like not logical that the train could be in a scenario where it somehow doesn't detonate, or somehow it doesn't detonate, but Einstein demands it, right? So back in the definition of simultaneity. So if we wish to describe the motion of a material point, we give the values, the coordinates, the function of time. Now we must bear carefully in mind that the mathematical description of all these has no physical meaning unless it is quite clear what we understand by time. We have to take into account that our judgments in which it plays part are always judgments of simultaneous events. If, for instance, I say the train arrives at 7 o'clock, and I mean something like this, that I'm pointing my small hand to a watch at 7 at the arrival time of the train, that's a simultaneous event. It might appear possible to overcome the difficulty of defining time by substituting the position of the hand of my watch for time. And in fact, the definition is satisfactory when we are concerned with defining time exclusively for the place where the watch is located. But it is no longer satisfactory when we have connected time in a series of events occurring at different places, or what comes to the same thing to evaluate times of events occurring at remote places from the watch. Now, this is extremely important, because this is the disconnect from the interpretation of absolute simultaneity.
Yeah. There's no concept of absolute simultaneity in relativity.
Well, if that were true, then, right, we couldn't have both the train and the stationary frame agree on the outcome. They would both have to lead to physically different events.
No, because I think the point that's being missed here is we need to clarify what triggers the bomb to explode in this scenario. Like, if we're trying to set up a paradox here where we arrive at two completely different outcomes in different frames of reference and only one of them can be correct, then let's go back and clarify for a moment what is actually the triggering thing that sets off the bomb here. So my question was, is it that the bomb needs to receive the two flashes of light at the same time in order to explode? I think that's how you set up the problem. But this is the part of, like, how do we want to set up the trigger for the bomb in this scenario? So can we say that if the bomb has a sensor on it, and if the bomb gets the two flashes of light from either side at the same time, then the bomb explodes?
Yeah, you can set it up in any configuration you want to. That's why I took it to the what's it called? To the
balls
balls,
and the lever.
yeah, to the balls falling, because it simplifies the matter, and the issues
Yeah,
like,
no,
well,
that
and
one's
then it's like, well, then it becomes the rigid body thing, but that's not the issue. The issue, like the issue philosophically, and like with respect, is that you're trying to preserve absolute simultaneity, and that's conflicting with the interpretation of relativity.
no, I'm not preserving absolute simultaneity at all here.
You said that you could have a scenario you said that the scenario was that both observers would agree on the simultaneous event when you account for
There,
the
it's not
timing
that.
difference, which is explicitly what Einstein just said, that a series of events connected no longer has any meaning to the observers because their time is independent.
So the thing that I'm saying both observers agree upon is if the bomb receives the flashes of light at the same time or not. Because if I'm watching the train go by, there's two separate questions here. The first question is, when do I see the flashes of light from the lightning strike? And the second question is, when does the bomb see the flashes of light from the lightning strike? So it's fine if me and the bomb see the flashes of light from the lightning strike at different times. The paradox would be if the bomb, let's say, receives the flashes of light from the lightning strike at the same time, but from my perspective, the bomb didn't. And that's the part which I'm saying there isn't actually any issue with. Do you mind if I pull something up on my end? Am
Yeah,
I
go
able
ahead.
to?
Yeah. Yep.
Yeah. You seeing the thing I've got drawn here? If I
Yeah.
do I have this shared now? Yeah, there we go. Yeah. So here we go. Here we got our two people, and the two lightning strikes that set off flashes of light, and one person's stationary and another person is moving to the right. And the stationary person is equal distance from the two lightning strikes, so they're going to receive those two flashes at the same time. But they're also watching the other person moving to the right. And the reason the person moving to the right is going to see one of the lightning flashes first before the other one in this perspective is because they run into it first. They're moving towards one of the flashes that's emanating out from the lightning strike on the right, and they're moving away from the flash on the left. So from, let's just call them, person A and person B here. So there's no confusion from person B's perspective as to why person A sees the flashes non-simultaneous, because person B sees that person A is running headfirst into the flash on one side and running away from the flash on the other side. So, person B is like, okay, I saw the flashes at the same time, but I can see that person A is not going to get the flashes at the same time because they're heading into an
Oh,
oncoming flash and away from
I
the
see.
flash behind them.
So it's an apparent effect then. Is that what you're saying?
So from person B's perspective, they would say that they are simultaneous, and they would say that person A is going to have the apparent effect of them being non-simultaneous. Yes.
Yeah. So now do you understand that Einstein just specifically said that it's not an apparent effect and it's physically meaningful? They're
Well,
not
so
connected to
now,
this. They're not connected to the series of events. So here's the thing. So that's why I took it to the balls dropping, because now we can do like a mechanical effect where, like, say we have dominoes laid out,
yeah.
and if they're, if the ball deviates, they're going to hit these dominoes and fall. So in one scenario, an observer would see the balls hit the dominoes and knock everything down, and the other would not see that. And that has to
Uh,
that has to be the outcome. Otherwise, the sequence of events, you're making it capitulate to the outcome of the stationary frame. So you're showing there's a difference between the frames. If they're not to be logically consistent, they
mhm.
have to. It dictates that they have two different outcomes. That's what Einstein is constantly coming back to.
So I didn't see your setup with the domino one, but the setup with the two balls falling on the lever was awesome. I really had to think about that one a lot. But I think you mentioned right there that in that case, someone could pick at the fact of being like, okay, well, you're assuming a perfectly rigid lever here. And if you assume a perfectly rigid lever where when one side goes down, the other side immediately goes up, then you've already assumed essentially faster than light communications possible. Because if we really had that, then I could like tap out, Morse code on one side of a lever and instantaneously have that, going up and down on the other side. But if we have the lever as something, flexible here, and let's just say something drops on one side of it first, um, it's basically going to bend down on one side here, and then that bending is going to have to travel through the lever. So we're sort of replacing the light flash with the physical, deformation of the bending, traveling very quickly, but traveling through the lever if it's not like a perfectly rigid object and needs to basically flex in order to begin rotating, because, it's
Yeah.
not going to just
So
move all at once.
So earlier, though, did you understand when that paper was talking about how no matter what you do to try to compensate for the timing difference to make the outcomes agree, the students like aren't correctly grasping it? Because this
Um,
isn't about the rigidity or the deformation. It's very simply about the mandatory two different outcomes. There's otherwise, right? For example, like hear me out. Say you have a
mhm,
stationary clock and a moving clock.
yeah.
Now you're familiar with the clock paradox, right? Now, before we get into acceleration solves that or whatever, let's just take the example and say that relativity is true, and we're gonna test it or whatever, right?
Mhm.
Now we got our clock. Now we show that this clock in motion is deviating. Now you're aware that Einstein's, in the way that the theory works, is you have to show that that stationary clock will show the reciprocal. It'll show that it deviates by the same amount of motion, and the clock in motion becomes undeviated. And no one's ever done that before, because that's it's insane. So
Of the like fly a clock around really fast and see if it's out of sync with the one left on the ground to talking about basically the time dilation,
right,
right?
and mathematically,
Yeah,
you would have to show that if the clocks that go out of sync that were moving, you'd have to show that the comparison clocks also went out of sync. Otherwise, those two frames would not be equivalent, because one would be an inertial frame, moving at a uniform constant velocity. The other one would be
yeah.
just stationary.
Although I think you mentioned yourself, what people bring up, which is the idea that if you're going to bring them back together, one of them did have to accelerate at some point. Because if they both were inertial frames the whole time, then they would just keep moving away from each other forever.
Oh,
So,
I can give
yeah.
scenarios where they're moving at a constant velocity, and that's not an issue. The acceleration thing doesn't solve it at all. And further, you would have to show it experimentally, because they say that the around the world time dilation clock experiment by Heffel and Keating in 1972 was proof of time dilation. But if you look at their comparison clocks, those didn't show any time dilation or any effects like that. So it's only a
Oh.
one-way comparison. So that's an asymmetry in the relativistic analysis for,
So yeah, and
What?
I mean, I've heard of that experiment that they put the cesium like ion clock on a plane and flew it around, and then when they brought it back, like I haven't dug into it, but the report was that the two clocks had been synchronized before one went up on the plane, and then the one that was flown around on the plane was delayed. Was behind the one that had been left on the ground, showing the time difference between the two of them.
Yeah, you should look into it. It's quite a tale. I only referenced it to give like face value or like benefit of the
Yeah.
doubt argumentation, not to like nitpick at it or whatever. But yeah, you should look into that one. That's a crazy one.
Yeah.
But anyway, but like just to show that the effect has to be reciprocal in the measurement, and I could show some documentation from Einstein, stating as such, where he's like the effect has to be shown with reciprocity, otherwise, it's not logically or mathematically consistent with the theory because it's about
You mean that
symmetry.
like
Of
while they're
frames.
in motion, that they both believe the other one is slowed down, right? Is that what you're
If
referring to as the
yeah,
reciprocity?
yeah, yes, yes.
Yeah, right. And then the apparent paradox is like, okay, well, if both frames were equally valid and they both saw the other one as ticking slower from their perspective,
Right.
which one actually has the time delay on it? And then this is something that people still debate, I know, as to what the best kind of resolution to this is as far as how to describe it. But you mentioned there yourself that like the main thing that then gets invoked is the idea that there is a breaking of the symmetry between the two reference frames because we're not just having the two of them moving with respect to each other forever. We bring them back together. So one of them had to accelerate or decelerate. And that is what breaks the symmetry between the two frames and where we make up the difference between the two of them. So, like, each sees the other as ticking slower while they're in constant motion, but then when one of them decelerates, it sees the other one as ticking faster. And that's the compensation that sort of synchronizes their stories by the end of it. But I may not be, doing a perfect job laying it all out, really quickly verbally like this.
Yeah, so
but yeah.
so that's if you conceive of a scenario where you have to bring them back together.
Yeah.
You could do it in a way where they're moving linear, doing constant uniform velocity away from each other,
Yeah.
and then send a signal at a certain time back to one another. And then by the time that they would get it, they would both be younger and older than one another. So it's still an unresolved issue. Like the only way people solve it is by like interjecting things like gravitational fields or acceleration and just saying, stuff like that.
Well, so let's even just kind of forget about relativity for a moment, and just even in the context of just Newtonian classical physics, like if you and I are, but with a finite speed of light, okay. So if you and I are moving linearly with respect to each other, and neither of us ever decelerates, to come back to rest with respect to each other, and we're sending each other signals, we're getting further and further away from each other. So there's going to be an increasing time delay just from that. So I'm not saying that this is all explainable by just simply the calculation of the travel time of light. But my only point there would be that even getting rid of like these extra effects like time dilation, it would still already be the case that if I'm watching a clock moving away from me, I'll see it slipping further and further behind my own clock just because there's a longer and longer time delay of me getting the update, of what the reading on that clock is, just because it's getting further and further away from me. So it takes longer and longer for the signal to get to me. So, hopefully that, is a pretty sensible example of a situation where two people would mutually see the other one's clock as being behind because they're both seeing the information on their clock immediately, but they're seeing the information from the other person's clock after the whole travel time of light delay because they keep getting further away from each other.
All right, let me read this example off to you. I have it up on the screen if you want to take a look here. So this is from A.G. Kelly. He says, "Let us devise such an experiment. Let the 5-year-old twins pass each other by in outer space while moving in a straight line at uniform speeds with respect to one another.
Mm.
They do not arrange to ever meet again. In this edition, the twin paradox does not seem to have been ever proposed to date. Assume that the twins travel at a mutual speed of recession of 0.9999999 c with respect to one another. If they continue at that speed for 60 years as understood by either of them, then according to special relativity, without decelerating or reversing the age of each person according, the other would be reckoned as 5 years and a month. This is not necessary, or it is not necessary for the two to ever meet each other or return to verify this. This calculation, according to special relativity, should be so. Now we have a problem. The aging has not occurred during any acceleration or deceleration phase. The different aging has occurred during uniform motion in a straight line with respect to one another. If separated, the twins from or if the twins had separated from each other in outer space rather than on Earth, it would have no weighing of which one was going away or which one was stationary. Thus, according to the other one is younger. So that's one
that's a good one.
possible that's one possible way of doing it. Yeah, he gives like several other ones, but yeah, like
So
I feel like the main thing though that we're kind of at an impasse on though, because it's not that it can't be calculated once the signal timing is corrected for. It's that that interpretation is not it's not logically consistent, that because you're correcting for the validity of the sequence of events in the frames, and if they're not valid, then there's a difference, and you're showing that there's not an equivalence between the inertial frames.
So just if I understood that last one, we have two people and we say, okay, they both start off at the same age and they're moving towards each other with constant velocity. And there's been no acceleration here. So they both should think that the other person should be younger, but they've both been moving with the same constant velocity, right up till the point they pass each other by and then go past each other. And I know in the last example I just gave, I was pointing out that even without relativity coming into the picture, there would still be a kind of apparent age difference or difference between two clocks just because of the travel time, of light and the signal delay. And even if you pass by someone, that's still going to be the case because, like, the moment you pass by them, it still is going to take some time for the light to get from them to you, and you're going to be moving on in that time. So there's always this problem of the signal delay. And yeah, I guess just sort of the broader point, I'd make, not having, the time or preparation here to go through all the math on it, that just might help people put all of this weird stuff with relativity in some better context, is that, like, none of this stuff about reference frames is, like, I don't know, literally real. Like when we're talking about space-time coordinates, it's purely something that we're imagining in our minds based on the information we're getting. Like, the only thing is the light signals hitting your eye, and then you're making an extrapolation. You're placing objects and events and velocities in this imaginary grid coordinate system, with the only firsthand knowledge being just, like, the signals that you're receiving at the moment you're receiving them, and then you do a calculation based on the time delay of the signal traveling to try to locate in the past at some distance away where you think something is. So kind of inherently, there's a lot of assumptions already in how you imagine placing things within a coordinate system. And I think maybe even more sort of a way that can make a lot of the relativity stuff feel a little bit even sort of more mundane is you could just say, well, it's sort of an artifact of where you would have to place things within a coordinate system to hold on to the assumption that the speed of light is constant. And then it's, if you do the calculation of how far away must something have been based on when I saw it, based on the assumption that the speed of light was constant, that then kind of draws the line backwards to place where it is in your imaginary, reference frame here for all of space. So, it's it's all built on that core assumption there, and and Einstein says it, that it's a postulate, it's an axiom, it's not experimentally testable, the one-way speed of light to begin with. Sorry, I don't know if that was directly answering the thing you brought up, but that's just sort of kind of the perspective I take on all this.
No, that was really all over the place and kind of inconsistent. So let me break down this, like the significance of this. So reference frames and coordinate systems are two different things. When we're talking reference frames, we're talking instrumentation, where the place is, where the measurement's being made. And in the theory of relativity is specifically talking about observational reference frames where, to put it in more direct terms, because it seems to be lost when people are talking reference frames, and you were mentioning defining things arbitrarily and where to put it and to maintain the constancy of C. Well, Einstein makes it very clear in his paper where his equations apply, and it says that anywhere that the equations of Newton, the equations of mechanics hold good, specifically right here. And then, so we're talking any inertial frame. So that's defined as being a uniform transitory motion, because there's no such thing as absolute rest, right? Because all these lads were Copernican lads that thought that the Earth was in motion. So to give a physically meaningful explanation to the Michelson-Morley test, right, for link contraction and time dilation to be meaningful, there has to be a disconnect from absolute length, absolute time, absolute relativity. I'm sorry, absolute simultaneity. So this theory being proposed was the same as Lorentz's ether theory, where all of these things where there's still an absolute theory, or I'm sorry, there's still an absolute simultaneity in Lorentz's static ether theory. The deviation that Einstein is putting forward with the same mathematical framework, just this is like the philosophical rules for how to engage, right? Otherwise, you're saying that time and space are absolute. So to definitively make the difference here, he says specifically that his equations are going to hold true for reference frames, like where we're taking measurements in frames that are in uniform transitory motion. So if those frames don't have a valid sequence of events, then they're not going to be physically different. They're not going to lead to a physically different outcome, and that means that relativity would be absolute, would be absolute. So he's saying that relativity is going to be not absolute. It's going to be relativity of simultaneity, right? So it has to be, in order for it to be valid, there has to be a different sequence of events. And then to continue off of that, he talks about the speed of light being independent of the state of motion of the emitting body or the observer. Now, he doesn't say observer in this sentence, but I think you would agree that it's about the observer and the source admitting the phenomenon, right? Like, or do we need to go into that? But I think you'd be on board with that. So in regards to the luminiferous ether, he's talking about a actual medium for the light propagation. And then when he's talking about an absolutely stationary space with special properties, or assign velocity vectors to a point in empty space where electromagnetic processes take place, he's talking about invoking preferred frames, or frames where no actual observer exists to take the measurement, and you're using some fictitious frame to have the motion be relative to. He's saying specifically not to do that, and then you have to do Lorentz transformations when you're handling inertial frames and the speed of light. And then he goes on to clarify in 1911 about link contraction and time dilation, because there was some confusion about people saying that, oh, they're not actual mechanisms, it's just like a philosophical thing. No, if link contraction and time dilation aren't measured in your frame, if that's not the actual explanation, then you have no no physically meaningful way to explain why Michelson-Morley didn't measure anything. So this has to be so Einstein goes on the record here to correct it in this. And he's like, yeah, you would absolutely be able to measure it. It's a real effect, yada, yada. So that was in 1911. And then again, which we already went over with clocks and how they're being defined, independent of simultaneous events. Like he's saying here, he even has a little preface here at the bottom. We shall not discuss the inexactitude which lurks in the concept of simultaneity of two events at approximately the same place, which can only be removed by an abstraction. Dude, no one's ever shown this. And to end on this real quick, Einstein in 1940, he reiterates This leads to the results of Lorentz transformations, talking about inertial frames equivalence and Maxwell's equations. So this leads to the result that Lorentz's transformations applied to space-time coordinates must govern the transformation from one inertial frame to another. And the content and restricted theory, one can accordingly be summarized in one sentence. All natural laws must be so conditioned that they are covariant with respect to Lorentz transformation. It follows from that simultaneity of two distant events is not an invariant concept in the dimension of rigid bodies of space, and clocks depends on their state of motion. So he's saying it right here that the simultaneous events is not an invariant concept. And at the end here at the bottom, he says once it was shown that simultaneity was relative and depends on the frame of reference, every possibility retaining action at distance in the foundation of physics has disappeared because that concept presupposed absolute simultaneity. So you're in philosophical conflict if you say that it's an apparent effect. You have to say it's a physically meaningful effect that has different outcomes.
So yeah, kind of what I was trying to say though before is I'm trying to be very careful here not to kind of ascribe too much physicality to any reference frame or any coordinate system, because it's not like there's literally a big grid out there in space for us to look at. It's all a mathematical mental framework for us to just try to make some sense of the information we have and sort of what we're seeing around the world. It's an inference. And there are features that could look like they're conflicting between two different observers' reference frames, when you draw out the grids of those reference frames. But the real question is there anything conflicting when it actually comes to like physical interactions, like the explosion of the bomb, is the great example there. And the thing on the whole simultaneity point is that relativity of simultaneity does not mean relativity of causality. And this is something that can be shown very explicitly in the Lorentz transformations, that while, yes, different observers may disagree on whether or not two events occurred at the same time or not, what they will not disagree about is whether or not one event caused another, or whether or not one event could have caused another. So, for example, if one light bulb turns on and then later another light bulb turns on, and the light from light bulb A reached light bulb B before light bulb B turned on, now we have a well-defined sequence of events, right? Light bulb A must have turned on before light bulb B because the light from light bulb A got to light bulb B before light bulb B turned on. So now that is a situation in which all frames of reference will agree that light bulb A turned on first, and then light bulb B turned on second. So if a light signal can go from one event to another event, then that causality is locked in, no matter all these other transformations of space and time between different reference frames. So there's a skeleton of a causal structure that is being preserved, even though there can be disagreement about simultaneity of events that are causally disconnected. So like with the lightning strikes of the two trees, if they're simultaneous in one perspective, one of those events can't affect the other, because what the light from the lightning striking one tree does not reach the other tree when the lightning strikes the other tree, and everyone will agree on that. Sorry, I cut you off. Go on to what you were responding to.
No, you're good. I just wanted to, because you're kind of like reiterating on my exact point that I mentioned earlier about something being causally linked versus a spatially separated event, which is what we went over earlier. So like causally linked would be like, life and death. You have to be born before you can die. You live your life and then you die, right? You're not dead and then you're born, right? So, but Einstein's making the explicit distinction here that that spatially separated events do not apply. And at relativistic speeds, you're going to have physically divergent outcomes. This is the philosophical conclusion of his framework, because what you were describing there of doing a summation of the frames to determine which sequence of events happened first, that's actually was Lorentz's theory, because this is his framework, like mathematically, right? But we're dealing with the philosophical deviation from it. I have here from the collected papers in what was it? Doesn't have the right year. This is when they were published or like republished or whatever in the 80s, but this is like the 1920s. Lorentz writes to Einstein and he says, "Hey, bro, do you think that there's like a universal spirit that's tied to everything that permeates the entire system under consideration, that keeps track of all these events, independent of states of motion?" Because the example he gives before for U and U prime is about moving clocks and how you could still use his framework to determine the sequence of events and preserve causality in that regard. And so he's like, "Hey, dude, like, what do you think about this?" And Einstein never wrote him back.
I
But
know
like,
that,
but
but
yeah,
you're very. I mean, this is a very.
you're having the same debacle. You're in the same predicament.
It's not a debacle because if you say the two events are spatially separate and simultaneous, then they can't be the cause of each other. Like one could not have affected the other if nothing can move faster than light speed. Um, so, right, so there can be disagreement about whether or not two causally disconnected events happened at the same time or one of them happened a bit in the future of the other. And it doesn't matter because they never affected each other. But if one event did affect another, which could, only happen, if there was at least enough time for a light signal to get from one event to the other. So they couldn't be simultaneous in any perspective if a light signal went from one event to another event, then that establishes a causal connection. And then connected to the fact that the speed of light then is taken to be invariant in relativity, that is what preserves the existence of causal connections. So, like if object A bounces into object B and then later bounces into object C, different reference frames will disagree on like how much time passed between the two collisions of object A smashes into object B and then smashes into object C. But they won't disagree on the ordering of events. Those are causally now linked events within a chain. So the relativity of simultaneity still allows for the preservation of causality.
They're not causally linked though. Like he's explicitly saying over and over again that they're not. And that was what that paper that I referred to at the beginning was saying, how just because you account for the timing difference, like it leads you to the conclusion that they're not going to have different outcomes, but that's not correct.
Simultaneous events are not causally linked. I'd need to go back and reread, the passage you put up there, but I thought that was what it was in reference to, that simultaneous events are not causally linked to each other. And that's why the ordering of them, is not preserved by the Lorentz transformation, that different reference frames can come to such different disagreements about did they happen at the same time? Did one of them happen before the other? But the important point is that regardless of whether or not disconnected events happened at the same time or one happened a bit in the future or the past of the other, nothing about one of them affected the other. But if it's a scenario where one event does affect another event, like a burst of light goes from one event and is the triggering initiator for a second event, then the second event is always in the future of the first event under all reference frames. So there's sort of like, if you list off all events and interactions between things, it kind of gives you like a skeletal graph of like what things caused what other things, and different reference frames will put that graph in different ways into a space-time coordinate system, but they'll all agree on what the connections are of like which event caused another event, even if they don't agree on how much time passed between the two events.
Right. So you could definitely do a summation of the frames, like I was saying, but the Einstein is saying like the whole point of the theory, like being different from that, because otherwise, otherwise you just are kind of believing a static ether theory. Then is that what you, or do you believe in that then, or?
Well, I don't even know what the ether is. I mean, that was maybe something else we could chat about after this.
Yeah, I think we've kind of reached the maximum conclusion here that we could get on this, but on this particular subject. But we could try.
Listening in on it.
Are you familiar
Yep.
with the Sagnac effect?
Yeah, a bit. It's the ring laser gyroscope, right?
Yeah,
The
yeah,
yeah.
yeah. So I came across a couple of papers recently that were trying to say that relativity of simultaneity was the explanation for the Sagnac effect, saying that essentially that if you were to take the reference frame of the observer on the rim of the device, you would see, let's say you were stationary, right? You would see like a perfect stream of
Mhm,
photons coming at you that would make like a coherent beam. And then if you
mhm.
started to rotate, the simultaneous event of the beam being split clockwise and counterclockwise becomes out of sync with respect to, how fast you're moving. So then you would start to see, instead of a continuous beam of light, you would see like spatially separated chunks based off of the timing difference of the uh of like multiple concurrent, simultaneous events being out of sync due to your rotation. Is that have you
Cool.
heard it
Yeah.
have you heard of that, or does that make sense to you?
Sort of, yeah, sounds familiar. I need to go back and review the details of the Sagnac effect. Um, but it was the point just that there's a particular kind of relativistic explanation for it. One that you want to get into or had contention with.
Yeah, if you're not super up to date on it, I'm not. We could talk about ether or something.
Yeah, that might be more, I
Although that is
uh
Sagnac adjacent,
it's
but
Sagnac
but in
adjacent,
a
right?
different context.
Yeah. Um Yeah. And maybe we can cycle back to in some future discussion if you ever want to have that, some of the kind of causality versus simultaneity stuff. But yeah, no, I'd really love to because I don't know how much time you have to keep going for, hit on things like ether, on um so there's something else I want to throw out here before we move past all of this discussion of the Lorentz transformations, which is the translation of one reference frame to another. It's what folds in all the changes in time and length and simultaneity and everything like that when you go from one reference frame to another. Um, so the historical story of this, right, is that Einstein postulates that the speed of light is constant, and then he works backwards from that to build out, or Lorentz had already discovered the Lorentz transformations as sort of what would need to be the case to keep the light speed of light consistent for all observers, regardless of their velocity. And then Einstein comes along and is basically willing to say, like, okay, I'm putting this forward as a physical theory of the world, that this isn't just a mathematical curiosity. This is how the world really works. But since then, something they didn't know at the time, but something that's now understood, is that the electromagnetic equations of Faraday and James Clerk Maxwell explicitly have the Lorentz transformations built into them. So the equations that describe, charge attracts charge, current in a wire deflects a magnet, all of the things that were done here with no concept of relativity, just the tabletop laboratory experiments of working out all the electromagnetic rules. Um, those equations are unchanged under a Lorentz transformation. So if you take those equations and you do the whole space-time dilating stuff to them, and the equations pop out identical to before. So, independent of the question of do Lorentz transformations actually describe the physical reality that we live within, it is a mathematical fact that the behavior of electromagnetism is invariant under a Lorentz transformation, that a Lorentz transformation changes nothing about the final outcome of what's happening in interactions between charges and magnets. So just I don't know if that's kind of a perspective on this that people are nearly as aware of. So I wanted to make sure to get that out there.
Yeah, no, good. That's a really good point. Do you know who Thomas Phipps is?
No.
Okay, so you know how so this is he was a mathematician who um did some work on He studied like Hertz's solutions and in his theory that he was working on for Maxwell stuff. And what he showed was that if you use an absolute, if you assume absolute time and take a derivative of that for like the moving observer or whatever,
Mhm.
you can adequately solve Maxwell's equations, his differential equations in the first order without using a Lorentz transformation, which is second order covariance. So if you need the speed of light to be the speed of light, then yeah, you could absolutely Lorentz it up and Maxwell it up for sure.
Yeah.
But in reality, like you mentioned earlier, um, the measurements of the speed of light are latitude dependent. Nobody actually measures the speed of light as being c. This is more of like a philosophical thing, and we could get into, and this like ties into the ether conversation actually directly, because it could be shown through interferometry that only, or the only way to actually predict the correct amount of fringe pattern
Mhm.
for the Sagnac effect, for example, is through classical equations that assume absolute space for the for the path length increase due to the motion, and without without doing a transformation that assumes a fictitious reference frame, which relativity is explicitly against, which we went over earlier, where it talks about assigning vectors to imaginary points in space. He's talking about using a transformation that's not that's not where the observational observer is. Like,
Mhm.
so that's the big distinction about his theory and his framework that is in direct contradiction. And like for things like GPS, they don't use Lorentz physics. It's all dictated by classic, and they use Galilean transformation between the ECI and ECF. 1 second, I got a phone call.
No problem.
Hola.
Appreciate everyone who's here listening in on this. My first time going live with all of this, so hope I'm doing a decent job, staying clear, keeping it interesting. Thanks,
All right,
everyone.
all right, I'm back. Sorry about
Cool.
that. Thank you, sir.
Yeah.
All right,
Well,
but yeah,
I mean,
but yeah, for the mathematical verification stuff of Phipps's work, I'd have to defer you to his work. It's obviously above my head, but part of what he was going over and what he shows, or what he's saying that he's showing, is like how he's solving the field equations without doing second order transformations and stuff. So if you would like to look at that, I think B said you were a math lad, if I remember correctly.
mathematical physicist, cosmologist. I would just say I spent a lot of time trying to find an example of someone who had repeated the Michelson-Morley experiment, like on an airplane. Very frustrated that I can't find anything. So there's a lot of really good questions that are being raised here, I have to say, of the types of sort of seeing is believing experiments that should be done that no one seems to have done yet. I'd love to see a lot of these things that were done on stationary to the ground, put on a train, put on a bullet train, now we actually have such better technology. We have trillion frame per second cameras that can watch, the illumination of light spreading out. If you turn on a light bulb, they can watch, the light moving. I mean, they're not measuring the one-way speed of light. They're measuring the cumulative time of the light from the light bulb to the surface it reflects off of to the camera. But you can watch, light, spreading out from a light source with these trillion frame per second cameras. And someone's got to like put one of those on a train and test out a bunch of this stuff in a way that's never been recorded before. So it's definitely something we could all come together on here. There's a lot of missing demonstrations here that someone should do, and we'd all benefit if someone could do them. Um, but yeah, ether. What's the ether?
Yeah, so I would say that is the vacuum properties of a vacuum, right? The dielectric permittivity and magnetic permeability properties are
Mhm.
the material properties of the ether. 'Cause
But
without
is the main thing just
the
saying that there is a preferred stationary objective reference frame, or is it
well,
adding something else?
well, it's several fold, right? Because in my cosmology, the Earth is stationary, and the ether is the dynamic cause of what's being measured with interferometry. So when they say, we're using this closed loop interferometer here, and we're measuring Earth rotation, and the way that they're doing that is they're measuring the fluctuations in the speed of light relative to their latitude throughout the day, and then they're plotting those minimum and maximum dimensions against sidereal time, and then they're making a sine wave out of it with the Fourier analysis, and they're determining that's Earth rotation. Whereas I would say that's ether rotation, and that's coming from the sky, and there's a translation of motion translating the medium that light is propagating through, so that
Wait, so
those
I'm so sorry, but so the
go ahead.
ether is non-stationary in your cosmology.
Correct.
It is so there's an ether like whirlpool basically over a
Correct.
stationary Earth. Okay.
Yes.
But okay, so then if you were, let's say, like on a bullet train or something, or just, like a fighter jet, and we had like a little miniature interferometer, would you then expect to see like interesting deviations from what we see on the ground? Because now you'd be moving against the ether in a different way than how you'd experience it if you're just on the ground, right?
Yeah, they do have those kind of fluctuations. Have you ever heard of like an inertial navigation, for example, or an inertial navigation system, for example? Let me see if I can pull up the
Yeah, it's
my INS
three
diagram.
like ring laser gyroscopes. I was just reading up on this, and a plane, right, to
Yep.
help the plane get
Yeah.
its pitch, lean, and yaw.
Yep. So check this out. When they do calibration for them specifically for a system for the first time, you have to remain stationary for like up to 48 to 72 hours, 72 being preferable. And the reason for that is basically it sets like a baseline calibration set, which it'll fall back onto because there's like randomized drifting and all these different things that it goes through. So like
Mhm.
yeah, like while you're like it's going to be calibrated in such a way that like latitude dependent fluctuations and stuff would be like would be zeroed out probably. So that would be not probably, that's how it would have to work if you were going to use it that way, and then like hide it. So that would and that's what they already do anyway. They have a system for that. It's called the Kalman filter.
Wait, I'm sorry to jump back to something, but if you're saying that there is an ether wind over the Earth,
Mhm.
then doesn't that imply that you would have expected uh, a positive result in the Michelson-Morley experiment on
Oh,
the Earth because it would pick
oh
up the
yeah,
ether wind?
yeah. There was. 1 second. Let me pull this up.
Isn't that such a famous null result experiment?
No, so this is their measurement right here, right?
Hmm.
Um, Now they predicted that they were going to get 0.05 of the fringe displacement, and they measured just over one fringes, and that's really important here. So let me read this section because it's extremely important, because there's a mathematical relationship between the fringe displacement and the square of it. And you could measure velocity this way, and this is really important because this equation that they use is actually the same equation that Sagnac used to derive the Sagnac effect. This is the same equation that they use in inertial navigation systems to this day. So we know that this interpretation of fringe displacement and motion is valid. So let's see what they say here. So it says, considering the motion of the Earth in its orbit only, this displacement should be 2d v squared over v squared, and the 2d is 11 meters for the wavelength, for the path length. V squared is Earth's orbital velocity, and then 30 kilometers a second, and then this is the speed of light. So this is just going to give them the ratio of the displacement. So it's going to be 10 to the minus 8 in the wavelengths there. So when you take that displacement, it should be, let's see, the distance d was about 11 meters, 2 times 10 to the 7th wavelengths for yellow light. Hence the displacement to be expected was 0.4 of a fringe. The actual displacement was certainly less than a 20th part and less than a 40th, but since the displacement is proportional to the square of the velocity, the relative velocity of the Earth and the ether is probably less than 1/6 of the Earth's orbital velocity, and certainly less than 1/4. Now, what he's talking about with this square relationship here is going back to going back to Fazal in 1852, with moving the translate or measuring the translational speed of water. they knew the ratios that they could get for the fringe displacement to the to velocity. So they established this relationship, that they still use today, but they just tell us that it's angular displacement, and they don't want us to like acknowledge the fact that the displacement is also the square of that is proportional to the velocity that's being measured. So what they actually measured was a velocity of 6 to 8 kilometers a second rather than 30 kilometers a second. So the dotted line would be the displacement if they were moving at 30 kilometers, and the solid is what they measured.
Mm.
And then these were repeated
Mm.
by other people. And then actually it was found that there was a periodicity to the measurement. So earlier when I mentioned that when they have a closed loop interferometer and they say that they're measuring Earth rotation and how they're doing it off the fluctuations for the peaks. So when you plot these minimum maximum peaks, you won't get anything off of this data set. This is just kind of like a randomized chunk of a fraction of what they did. But when you take like a larger data set, like Dayton Miller did, for example, or Hector Minera, what you'll get is the minimum and maximum peaks throughout the day. It's measuring the same thing. It's measuring sidereal fluctuations that correspond to sidereal time. So, but they don't want to acknowledge that with the interferometer that's configured at a right angle, because it's associated with Earth's orbital velocity.
Just to
they
make
try
sure I
to-
understand, if you go back to those, so the black line is what they measured there,
Yes, yeah, the solid.
and you're
black
saying,
line.
okay, there actually are these slight daily fluctuations within it, but they're smaller than the expected amount. And is your claim basically that what people have written off as like noise is actually a signal of confirmation of a slight amount of ether drag or ether wind effect? Or am I
Yeah,
misinterpreting?
no, yeah, you're pretty much nailing it. So let's see here. In modern experiments, right, what they'll do is they'll do Michelson-Morley experiments in a vacuum, or they'll use
Mhm.
they'll use different mediums. They'll use different shieldings for the interferometer, etc. And what was found experimentally is that the fluctuations can be reduced by the shielding type that you're using and the medium. So if you're doing it in a vacuum, you get less of the fluctuation variance, and it's actually falls back on the Fresnel formula from 1818, where he derived the hypothesis for Fresnel drag, where he said that the density of ether in a translucent medium would be proportional to its refractive index squared, and then from that he derived how much a medium would drag ether, based on that. And then in 1852, Fazal measured that with water using those ratios. So if we kind of follow the logic about ether density and proportionality to refractive indexes, um, that would kind of go in line with the sensitivity of being able to make the measurements of the fluctuations, versus, not being able to do it, because when the experiments were repeated by other people, they get the data that confirms what everyone else measures with their closed loop interferometers.
Mm. Cool. I don't know if I'm being disappointing here as a debate, partner, but I'm very
Oh no,
cautious against,
no, you're good. This doesn't have to
arguing
be.
anything I don't feel totally secure on. And like, you're doing some really deep dives here into like the data analysis and experimental setups of all of these things. And like, I'm not an experimentalist. I mean, I know that you're coming to conclusions that are dissenting against the conclusions that the rest of the community, in the research field, has come to, and that's kind of the point of what you're doing here. I don't necessarily put, science is not a democracy here, and I appreciate, the magnifying glass you're taking with all of this, and kind of questioning how the data has been read. So definitely, if we'd ever chat again, I'd love to read up a little bit more on kind of the details of all of this.
Absolutely. If you ever need any papers or anything, just ask me. I got a whole database.
Yeah. Yeah, very cool. Yeah, I should say, in my background, it's very much into theoretical cosmology. So, it's like on the kind of course track of going through college and grad school, it's like they say, like, Michelson-Morley experiment, null result, special relativity, like that's all like half a lesson. It's like moving
Right,
on,
right,
to the
right.
next thing. And then I didn't specialize as an experimentalist. Like I wouldn't know the first thing if someone handed me one of these apparatuses. I'd drop it and break it. So I delved off into just kind of a theoretical study of the math of the models that were the victorious models, that the community, came around on, throughout the 20th century. And I've never seen anything personally that has given me much doubt in the usefulness of relativity as a tool for describing reality. Though I do love a lot of the especially the lever thought experiment was a really great, kind of attempt to find a paradox there. But I will say that I'll just say that, like, from an inside perspective, I see that cosmologists are only humans, subject to groupthink, subject to career advancement over good science, hostility to dissenting opinions, and like. I don't think I have the same criticisms of modern cosmology that you have, but I'd just like to state for the record that it is a teetering tower. It's fragile. It's assumptions built on assumptions, and there can be, confirmation bias running throughout. And like my main thing of where I really dissent from the broader cosmological community is I do not think that the evidence is there for dark matter in the way that most people have rallied behind it and
Nice.
been very, very hostile to opposing views on that. So yeah, I see this stuff, and one of the things that got me interested in kind of getting involved in these types of discussions is, I didn't like when sort of, I guess, my side, the Globers, the defenders of mainstream science would, come out extremely absolutist on topics on the fringes of physics that I just do not believe are properly supported, or that we really have a high confidence degree on what the data is saying. And just the last point here, I know I'm sort of transitioning topics, is that, like, yeah, I mean, no branch of science should ever be framed as the absolute truth, because, you could always have a new theory that blows the last one out of the water. But, like, in cosmology especially, we're so limited. Like, in chemistry, put a chemical in a test tube, heat it up, spin it around, put it under pressure. You can't do experiments on the cosmos. I can't take a galaxy and put it in the microwave to see what happens. So, like, the cosmologists should be the most humble of any branch of science because they're so experimentally limited. They're just looking at data from the sky. They can't test it. They can't experiment on the things they're looking at. But instead of being the most humble, they've kind of reacted, in my opinion, as being some of the most sort of aggressively arrogant. So just on a point of commonality, I feel the frustration that a lot of people have kind of growing up seeing Brian Greene and, Neil deGrasse Tyson go on TV all the time and just make these really huge assertions that we, like, know for sure things about objects that are meant to be X number of billions of trillions of miles away. And at a certain point, you're like, how the fuck do you know that for sure? And, and they don't, because it's models based on models based on models. But, obviously we started off here with me defending that there were resolutions to some of the apparent paradoxes in the model of relativity here. So I'm pretty ADD, if you can't tell. My brain jumps around to a lot of different things. So I turn it back over to you of anything you want to get into and whatever time we have left.
Yeah, thanks for coming on, man. I appreciate the back and forth. Yeah. It was a great conversation. Look forward to talking to you more.
I mean, there's lots of different kind of branching things within all of this. But to get back to something just on I've heard lots of different things of people talking about ether theory, and they often point to you as, like, the main guy on this here. But the main takeaway I'm getting from it is the importance of a stationary reference frame, or sorry, an objective stationary reference frame, as opposed to equal validity of all reference frames. But Other people have also said that like the ether is meant to be a unification of all the forces, that it's meant to explain gravity as well. Do you have any comments on that? Are there other goals here that it's meant to explain?
Oh, so yeah, you can like mathematically introduce different causal mechanisms for gravity or whatever. So like I don't focus much on that. I more
Mhm.
focus on the velocity measurements because that's an important thing. That's like an absolute measurement. So
Mm,
that's mostly where my area of it is focused on. That's the most
Gotcha.
tangible part of it. And then in terms of being stationary, um, that can be shown, through dynamic analysis using, Newtonian equations.
Mm,
So uh, that's not necessarily that wouldn't necessarily be mutually exclusive to an ether, right? Like if the Earth were in motion or whatever, I mean, you could do something like that or whatever. But yeah,
mm.
that's why I made it specific that the Earth is stationary in my cosmology and that the ether is dynamic.
Would it still be appropriate though to think of the ether as being like a field in the way that physicists talk about the electromagnetic field, or is there some um, kind of additional postulates that you have about it? Like, is it
So
made of anything specifically?
so I know that the material properties of it, well, the vacuum properties, like I was saying earlier, that would be what I would say are the material properties of the ether, right? Like what is it made out of? Like I don't know, some primary substrate, fundamental
Yep.
thing. Like it would be the same thing that what it all comes down to for like the baseline of a theory where you got to have a fundamental, right? So mine would just be like there's a primary substrate that everything is made out of that
Mhm.
all would be traced back to the same thing. And then the material properties of that are measured, in a vacuum. And then so check this out. When you go to altitude, there's like a velocity gradient. So when you're at 200 feet above sea level, the ether velocity, as measured by Michelson and the boys, is around 6 to 8 kilometers a second. But when you go to 1,800 feet above sea level, the velocity goes to 8 to 12. I'm sorry, goes to 10 to 12 kilometers a second. And that was confirmed by another person in two separate locations, a guy named Yuri Galev, 30 years after the first guy that did it. But yeah, it seems like there's like a gradient to it, then if the velocity is getting faster up there. So,
As would be so have people done interferometer test at those higher altitudes?
oh yeah, yep. There's a guy named Yuri Galev in 2000. Well, he did this test in like 1998, 1999, or I'm sorry, 1999, 1998. But he published the
Mhm.
stuff in like 2002 to 2004. And yeah, he did several sets of measurements. One was with an optical interferometer, so with the classic laser beam setup, and then he did a radio link setup using millimetric radio waves, using
Mhm.
two different setups so that they were one-way measurements, and then he compared the differential from them and found like a matching periodicity that like the periodicity that gives the velocity boost versus the retardation to create
Yeah.
the measurements that they all measure to get the sidereal fluctuations. Yeah, anyway, he got one-way measurements of that. It was going there and back, so it was really cool.
Cool. Yeah. I want to ask a little bit more, I guess, about gravity specifically, because that seems to be a very contentious topic, within this community, as far as, I've seen of, so I sort of wanted to get your take on it, uh, gravity is an interaction of massive bodies attracting other massive bodies. Um, do you do you agree with that? Do you have an alternative explanation, for why things fall to the ground? How does that fit into the ether cosmology?
Yeah, so I just go with the classic flat Earth interpretation of let's see, what would it be? We have an electrostatic gradient that gets stronger at altitude. It's a linear gradient. So that would be the mechanism that creates like a downward flow for things.
Ah,
But
okay, yeah, good. So we stumbled upon another thing to we could dig into, or save for a different discussion. But glad to strike upon this. Okay, so if you're going to try to explain the falling of objects with an electric force, we've got neutral objects. We've got positively and negatively charged objects that would be acted on in exactly opposite ways by an electric force. So, like, under such a model, wouldn't that mean that, like, only positive objects fall down, but negative objects should fall up against the voltage gradient there? How would you explain that?
I wouldn't.
Okay. I mean, like, what about like a neutral object? Like big hunk of bricks or something. You take your electrometer. No significant amount of electric charge. Whatsoever within it, and it's still false.
Yeah, so I'm not super up to date on my gravity mechanisms.
Yeah. No,
Um,
that's fine. Yeah,
I don't know.
that's totally good. I just was curious if that was a strong part of this for you, or if that wasn't the main kind of aspect you were focusing on. If the main aspect was more the kind of relative velocity stuff and frames of reference part of it, or if this was
Yeah.
also strongly connected to theories of gravitational attraction.
No, not at all. Because I've seen it derived through electromagnet or through magnetism, specifically through electrostatics. Like I said, I don't know the full explanation to answer the exact question that you have. There is an answer for it. I'm not the guy to answer it. But
Yeah.
there's anyway, but you can describe it through different ways, and I think that that's part of the battle, right? Is like the people that got there first with the Cavendish Newton mass attracting
Mhm.
mass story kind of like planted the flag in it, but nobody really knows. So like I don't think it's something that we'll ever be able to determine, because we're nowhere closer to determining it. Because like at the experimental levels, like if any of that were true, then Michelson-Morley would have measured 30 kilometers a second, due to that velocity based on the mass attracting mass relationship as applied to the sky through the algebraic shuffling of Kepler's laws. So like when it comes to like what is gravity, why does it fall? Like I'm like, I don't care. You can kinematically derive it as an acceleration over height and time, so it doesn't.
Yeah.
Like why does it do it? Like couldn't tell you.
Right. Well, I think that the falling things then is less interesting to this than the Cavendish type experiments of measurements of a slight attraction between massive objects to each other within the laboratory when you control for the amount of charge on those objects to try to isolate out other possible sources of interference and forces. Yeah. Certainly, maybe just to cap off on that, the aspiration for some unified field theory of all interactions, that's the holy grail, right? Everyone wants to put it together in some way and have some common explanation rather than this kind of what can feel like a very ad hoc mixture of different phenomenon explaining different parts of the universe, in different ways. That would be great if it all unifies together in some way. So I was just sort of curious how much kind of ether cosmology shares that motivation, to find the fundamental substrate of reality. Is matter made of ether?
Yeah.
Okay. So it can be a substrate for all things, medium for light.
Yeah,
Fundamental thing.
there's a model by Atutovsky, this Russian guy who came up with this toroidal vortex structure model for ether flow. So he
Yeah.
would, so like basically starting with like the measurements of a proton, you would take the vacuum permittivity and magnetic permeability values and set up like a density gradient of ether essentially, and then from that he like relates the measured values of a proton to some toroidal stuff that I don't quite get, but basically it's just open interpretation really on that, but there's models for that kind of stuff.
Yeah. Um, uh, well, I might need to get going in a bit. Really appreciate the conversation. Did you have any last kind of thoughts for me on anything in the standard cosmology? You've got an axe to grind against that you were interested in bringing up, seeing if I would be pro or against.
Oh no, I can't think of anything right now.
Maybe next sometime we'll talk about, expansion, Big Bang, I gotta say, there's quite a startling disconnect often between like what is presented in the CGI animations that get fed out to the public versus like what's actually in the models of, what physicists are describing, which is just super frustrating to deal with, that the community is so poor at even representing accurately what is described by the math, or maybe the people working on it haven't thought about it critically enough to realize how poor the representations, the animations so often can be. Like, oh god, you see a million times the whole like Big Bang animated is like there's a little speck and then kablooey, and that's like not even what the math is describing. And the whole thing is ridiculous from that perspective, that they would choose to animate it in such a unhelpful way, even to help people get to grips with what the model is describing, let alone whether or not that model actually is supported by the evidence. Well, if you don't have anything else, really appreciate the conversation. We can end off here and hopefully have another one. And I just want to share one little anecdote from my time in academia that I think you'd appreciate, is that at the university where I got my PhD, just graduated, defended my thesis last summer. One day at the Friday colloquium talk, where like people are presenting their research, one of the old tenured, retired physicists who like no one had seen in years, basically, just stuck to the basement, didn't really teach any classes anymore or anything, comes out with essentially an ether theory. He called it a universal torsion field. He was going up against just special relativity. Like, he was wiping the blackboard clean on all of that. He had alternative explanations for everything, preferred stationary reference frame, particles as vortices in this torsion field, an explanation of time dilation effects for like the radioactive decay of particles, where like one of the big proofs of time dilation is that a stationary radioactive particle decays quicker than a moving one. So people are like, okay, the moving particle has its time slowed down, and that's why it doesn't radioactively decay as fast. And this professor was like, no, it's that the vortex structure of the particles are more stable when they're in motion, and that's why they don't decay as quickly. So we don't even need time dilation for it. And definitely a lot of very wide eyes in the audience. So, I guess with some of the criticisms I hear of academia, it's like, yeah, some of it's very real. Some of the very kind of aggressive kind of group thinking policing of things, particularly on certain subjects, is like definitely there. But like it's a mixed bag. There's also like the interesting oddballs, with their wildly alternative theories, all over the place, still holding down their tenured jobs. So, it's, it's an institution made of human beings like any other one. Anyway, really, you know what? I will try to find that paper on the universal torsion field, Alan.
Dude,
I'll send it over
please,
to you.
that
I think
sounds awesome.
you'd really
Dude, that guy sounds like a
it.
legend. That's hilarious
Oh,
because
yeah,
Ben
me and
said
all
the
the other
same
grad students
thing
loved it. It was the
about
whole talk that
muons.
night. Yeah, because we all, like we'd go out drinking, the night after on a Friday night, weeks over, and like that was all anyone could talk about, and people were amused, and I just think like they didn't really know exactly what to think about it. It's like, okay, is this guy onto something? Has he finally lost it? Is this legit? What do we make of this? So it's important to keep, every a fruitful place for alternative theories to sprout. But anyway, yeah, dude, thanks so much, and hopefully we can do it again. Really great to meet you.
You guys should have banded together and overthrew the establishment and made him your ruler.
So my advisor in grad school was not that alternative, but still decently alternative, because he was a fairly big anti-dark matter cosmologist type who also was like a real character within the community on his own track of thoughts. So that was, who I got to learn from, and, just get to see these things from a lot of different sides. But yeah, anyway, thanks so much.
Yep. Later, man.
All right. Peace. Thanks, everyone.
Right back. I'm gonna close YouTube. See you guys later tonight for the Ruhif Fest with the Celestial Theodolite.